Absolutely.
Okay.
Are we good?
Yeah, we're good to go.
This is Mary. Well done. How you doing?
Fine. Good afternoon, everyone. Rudyard, please, can you make others co-host so that they'll continue with the admission?
Which mission? No?
With the admission.
Okay. All right.
I'm going to do that. Can continue
Okay.
at the meeting.
Okay. Thank you. So, good day, everyone, and welcome to the first collaboration event of SCG Nigerian Student Section. And on this phase, we are kicking off with the technical workshop on seismic method. So my name is Chinaza Ebere Arukwe. You can simply call me Naza or Mary. And I'll be moderating this section with my two other friends, Rodiat Oyeyemi Amusan from Federal University of Technology, Akure, and Iburizim Ozoma Power from Federal University of Technology, Owerri. Yeah. So, and myself, I'm from Nnamdi Azikiwe University, Awka, Nigeria. Yeah. So we are on, and I'm excited that we had over 300 applications for this event, and that's a good one. So we have like a host of activities in line for you, starting with the technical workshop that we're kicking off with the live section today, the challenge bowls, the career fairs, the paper contest. So we just need you to sit tight and enjoy and learn while we keep ourselves abreast with geosciences amidst the ASU strike, so that we don't forget entirely everything we are taught in class. Yeah. So for the program, the outline will go like this. Gospa, please, can we have the next slide? So the outline will go with the icebreaker section that we're already in. So please, as you're joining in, you can just put on the chat box your name and the school you're joining in, so that we can just recognize you. And we'll now go to the brief introduction of the speaker, the first lecture, the question and answer section, and the membership as well, and then we can now close. So for the icebreaker section, we are already in it. Yeah, Joshua, thank you, but you did not add your school. For the icebreaker section, we're already in it. So I'm just going to be giving us, I'll just be reiterating the modality of this workshop, everything you need to know about the workshop, and what you need to do to get certified from the workshop. Yeah, I can see Akiyemi, Demi, most guys from Futa, you guys are all welcome. So for the workshop now, the workshop is meant to have 5 live sections, yes, from the introduction to the application. Rakib, I can see you from Futa. So from the introduction down to the application of the seismic methods. So for the workshop, each live section has a quiz attached to it. And this quiz will come up 2 days after. It will be published on the Google Classroom 2 days after the live section. And you also have 2 days to attend to the quiz. And the average of the quiz are meant to be 5. So from these 5 quiz, you're meant to have an average of 70%. Yeah, welcome, James from Unilag. So you're meant to have an average of 70% for you to qualify for the certificate from the workshop. Then the workshop is going to be, the live sessions will be holding on Saturdays and Sundays. So our first live section is today, Saturdays by 9 a.m. West African time, and Sundays 3 p.m. West African time, just like we're having it now. Then all other informations like the quiz, the quiz, the recording of this video will be published on the Google Classroom. So it's very, very important that you make sure that you're on the Google Classroom, because a lot of information are going to be passed on there. So yeah, in subsequent time, if we have further announcements, we'll make it known to you. So without much ado, we'll be going straight to the brief introduction of the speaker. Gospel, can we have that slide? Yeah, I can see so many people from Unilag, Futa, Footmina. You guys are all welcome. Okay, so here is the slide. So we have, trust me, we have the best hand for this job. So our host, our tutor is Deepak Kumar. Deepak Kumar is a research scholar at National Geophysical Research Institute and a geophysicist with a strong background in conventional and multi-component seismic data analysis, velocity modeling, full waveform inversion, seismic anisotropy, gravity modeling, heat flow modeling, and lithological interpretation. His PhD thesis alongside 2 papers are under review, while having published an article in the Journal of Asian Earth Sciences. He recently submitted another paper on seismic anisotropy to image Halley discontinuity using a component-wide single seismic data. Deepak has many awards to his.
Wait, I don't understand. Saying that this man.
Deepak has many awards to his name, amongst which the Young Scientist Award that he won at the second Triennial Figure International Conference held in October 2019. He was also selected for the SCG SLS program to attend the SCG annual meeting in San Antonio, Texas in 2019, and he won the top ranker certificate of excellence at the symposium. He also got a certificate of merit and a gold medal for securing the first rank in his master's program, which he did in marine geophysics for the academic year 2013 to 2014 at the Andhra University, and many other awards to his name. So ladies and gentlemen, with a clapping ovation that you can just drop it on the chat box, kindly welcome our instructor for today. Yeah, thank you very much, sir. And the mic is yours now.
Thanks, guys. It's really good to talk to you guys, and you guys are. One second, yeah. So it's a pleasure to meet you all, and you guys are doing a wonderful job during this strike going on. As Rodia told me that you guys are having. Yeah. So this is a wonderful initiative to learn and to keep learning and motivating yourself. So with this, I would like to share what would be our coursework. So today I'm going to start with a brief introduction of seismic method and what are the different types of waves which we deal with, and types of seismic method based on our objectives. So today's session will be on the very fundamentals of seismic method, and then we'll move on to data acquisition, how the data acquisition is planned and how it is done, executed. And then we will talk about, one second, someone, yeah. So then we will talk about the real data set, like for reflection method and refraction method as well. And then we will move on to, then we will move on to, different free softwares for processing and interpretation. So at the end of the talk, I'll tell you which softwares you have to download and which softwares which you can apply or get from industry for free under student license. Okay. So with this, I'm going to start my talk, and let me share my screen. Now, yeah, hope you can see my screen, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. And am I audible and can you comprehend what I'm trying to say? Since my voice is not breaking in between, right?
Yes, sir, we can hear you.
Okay, great. So today we'll talk on about introduction to seismic method, and I'll be keeping the presentation very basic so that you can follow, and it will be an interactive session so that whenever you feel like that you don't understand, you can interrupt me and you can ask me questions, and even I will ask questions of what I'm trying to teach, whether you are getting or not. So it will be a kind of interactive sessions. So let's keep it interesting and let's move on to the first slide. What happened? Yeah. So what is seismic method and why we study seismic method? So the seismic method is nothing but the study of seismic wave or pulses generated in the earth or velocities, so that we can try to image the subsurface. Now suppose if you go to now suppose if you have a broken bone or something, so you go to a doctor, right? And what doctor suggests you to go through an X-ray, right? So what happens during X-ray? So they put your broken arm or leg in just beneath the X-ray, and the X-ray images your broken fractured bone, correct? So the same application is used here, that we use active source of passive source like earthquake. Passive source means earthquake, or active sources like dynamites or vibroses or thumper. So we use those to generate seismic wave through the ground, and we record it on the surface with the help of a geophone, and then we study the path followed and the velocity of the seismic wave and how many layers it has gone through. Means it has gone down and it has reflected and refracted and come up. So we study seismic wave to image subsurface. Now here you can see, let me do one thing. Okay. Now here you can see an image. Who can tell me how many layers are there in this particular image? Kindly unmute yourself and anyone can answer that how many layers can you find in this particular image? Hello?
Yeah, I think we have 9.
9 layers.
2 layers.
No, 2 layers. Not. I'll show you that. See, this is the first layer, correct? You can see some kind of boundary here, right? Can you see?
Yes.
Yes, we can.
And then one more boundary is here, which you can see clearly. And then one more boundary is here, correct?
Yes,
Can
we can see. We can see.
Yeah. So there are 4 layers, right? But how? Because since we cannot see beneath the surface, so how will we image the orientation of the bed and to know what depth a particular layer is located? So for that, we use seismic method. So so what are seismic waves? Seismic waves are nothing but a pulse of strain energy, or it's an energy which propagates through solid and fluids. Okay, so seismic waves are nothing but a pulse of energy or a pocket of energy which travels through the surface or subsurface, and it is recorded on the surface, and after the analysis of that, we'll be able to image the subsurface. Correct? Clear? Are we good? Up to here, correct?
Yeah, we're
Yes, sir.
good.
I think we're good.
Yeah. Okay. So can I move this? So seismic method is the most accurate method to image subsurface, and with the help of seismic method, we will be able to delineate between fine structures, because like seismic method is an active method, and passive method is seismology, which is done by studying the earthquake waves or seismic waves generated during an earthquake. But in seismic method, we generate artificial seismic pulses or waves using thumper, vibrosis, dynamites. So depending on our objective, what we want to study and what is the depth of my investigation, we use sources according to our depth of investigation. Now, suppose if I want to study the full crust, like up to 30 or 40 kilometers of the depth, so we go for dynamites of huge charges, like around 100 tons or 1,800, 1,000 to 200 kgs of dynamites or explosives. But if my depth of investigation is around, per se, suppose 3 or 5 kilometers, 3 to 5 kilometers, then we'll go for thumper, vibrosis. Okay. And now suppose if my depth of investigation is even less, like less than 1 kilometer, then we'll go for sledgehammer. Okay. So which you might have, studied, or in the last presentation, Kenneth, my good friend from Wits University, Cape Town, South Africa, he might have told you that they use a sledgehammer to study seismic wave for mines, to image mine mineralogical structure in mines, correct? So as I said, seismic method is the most accurate method to image subsurfaces, structures like salt domes or any kind of fault, or anticlines, synclines, reservoir, mineral deposits, or even the properties of the rocks in situ. In situ means a thing which is present there, means like we don't have to bring it to our lab and then we generate artificial environment of the scenario of the, from where we have rocks, and then we generate the seismic wave in the lab and then record the output and then do the analysis. So instead of doing that, seismic wave can help us decipher the physical properties of the surface of that particular rock types or lithology in that particular area, which we will see in the coming presentations, like when I'll be talking about my real case data for reflection and refraction method. So types of seismic waves. So whenever you feel like I'm getting far and you cannot able to comprehend, please tell me and ask me questions. Okay. So what are the different types of seismic waves? So there are basically two types of seismic waves. First one is body waves, and second one is surface wave. Again, body waves are of two types, like P and S. Okay, because they generate through the subsurface, and surface waves are also of two types, rally and love wave. They propagate along an interface or surface. Okay, so now first our main focus will be on body waves, because since we are talking of seismic, active seismic, and their uses in industry and academia. So we'll be focusing mainly on body waves, that is P and S wave, even though surface waves are also studied for near surface geophysics. Okay, but since I'm not an expert in that, so I'll not be talking about surface wave much, but for understanding, I will be discussing here. Yeah. So the body waves are of two types. First one is, yeah. Anyone have any question? No. Okay. So kindly unmute mute yourself, and if you have any question, then unmute and you can ask. Okay. So body waves are of two types. First one is P wave or primary wave or compressional wave, because P wave is called primary wave because it is the fastest wave to arrive on the surface and recorded by the geophone. So the first wave which is recorded at the geophone is P wave. That is why it's called primary wave, and it's also called compressional wave because they move through a medium in a compression and dilatation form, or compression and rarefaction, you can say. So you can see here, this is the propagation of P wave. You can see here the compression and rarefaction or dilatation. So it moves like a spring. Now suppose if you stretch a spring, what happens? it compresses and then again it dilates. Okay, so whenever seismic wave move from one point to another, so what happens is it hits the particle, and then the particle goes into compression and then rarefaction or dilatation. So with compression and dilatation, it moves ahead. So the motion of the particle for P wave, it will always be parallel to the direction of propagation of wave. Like if P wave is moving towards this direction, the particle motion will also be in the same direction as the P wave. Okay, and P wave can be given with the P wave P wave velocity can be given with the help of these three parameters or four parameters. You can say this is the Lammers constant. Okay, and which we will see how we can derive P wave from density from P wave in the coming presentations. Okay, so we need three parameters or elastic constants of parameters for the giving P wave velocity. So one is first one is Lammers constant, and then this is shear modulus, and this is the density. And also we can have compressibility, that is compressibility K, or shear modulus or density. So this is the formula to represent P wave velocity or to delineate P wave velocity of a particular layer. If these elastic are given, these elastic constants are provided, so we can easily compute Vp. So far so clear, correct? Now moving on to the next slide. Now S wave is the secondary wave or shear wave, because their ability to be to propagate only in solid media. That is why they are called shear waves. Okay, and these waves reach the geophone or recorded in the seismogram after P wave. That is why they are called secondary wave. And S waves are very useful for the study of study of seismic anisotropy, and also to delineate any kind of fractures. Now suppose S wave given by only two parameters, that is shear wave, shear modulus and the density. So that means S wave is mainly dependent on shear modulus and density. Now suppose, can anyone tell me what is the shear modulus for fluid media? Can anyone? It's 0. So that means shear modulus, now suppose S wave velocity is directly proportional to shear modulus and inversely proportional to density. So if for fluid media, if this is 0, so what will happen? Bs will become 0, correct? Correct? I hope.
Yes.
Yeah. So that's why. Now suppose if there are many fractures in the subsurface. So what happens? Fractures have either fluid, fractures have either liquid or air in that, or it has any kind of fluid in it. Correct? So what happens whenever S wave passes through a subsurface and encounters a fracture? What will happen? Either it will not be generated in that fluid media, or what happens if there are many pores in subsurface and the pores are filled with fluid, any kind of fluid. Okay, and so now suppose there is a rock. Now suppose this is a rock, and these square shapes are pores, and these lines are matrix, like solid material. So what will happen whenever S wave will travel through this? So it will not be generated or propagated in the square boxes which are pores or filled with fluid, and it will only be generated through the matrix. That means these black lines, correct? So what will happen? The S wave velocity will decrease drastically for any kind of fluid media, okay, or with a rock having any kind of fluid pores filled with fluid in it, correct? So P and S wave data, like P wave data and S wave data collectively will give me lithology, which we will discuss later. So, and also as we can see here, the S wave, the particle motion for S wave is like longitudinal wave, like light waves. Okay. So what happens? The particle motion for S wave is perpendicular to the, now suppose this is my propagation, wave propagation direction. So particle motion will be perpendicular to it. So this is also called longitudinal wave. Okay. So far so good. Okay. And surface wave. Surface waves are Rayleigh waves, and as we can see here, we'll not be discussing about surface wave during the course of our workshop. So just for basic understanding, I'm discussing it here. So as you can see here, there is a quenching and like wave kind of motion. So there is quenching and dilatation, and wave kind of motion is happening. So the particle motion associated with this Rayleigh wave is retrograde, means like it will compress and dilate and quench. Okay, so with this, the particles are particle behave when a Rayleigh wave passes through the surface, and it propagates only on the surface of the wave, and it cannot propagate in deeper section of the earth because amplitude of the wave decreases very exponentially as with depth. That means the energy of surface wave dies out or dissipate drastically as we go down. So, and this is these surface waves are generally studied for near surface surveys or analysis using MASWA. Okay, and the velocity of this Rayleigh wave are slightly less. So we'll be seeing the position of PS and surface wave in the coming slides. So P wave is the faster than S wave, and then Rayleigh wave is the has a slightly less velocity than S wave. And then there is love wave. This is called love wave, but this is the most dangerous wave. Now suppose whenever an earthquake happens, so body waves are not that damaging as compared to the surface wave. As you can see here, the particle motion is like this, means it displaces the particle from on the surface like in a zigzag pattern horizontally. So it causes the maximum damage to the property during an earthquake. Okay, and yeah, and it's really it's slightly faster than the Rayleigh wave, so it comes between S wave and Rayleigh wave. Okay, now you can see, can we make it as a list? Okay, yeah. Now you can see here, this is an actual seismogram, okay, recorded for the 2001 earthquake of Peru, of Peru, and with magnitude of 8.4. So as you can see here, this is 10 meters. Now suppose earthquake happens and after 10 minutes it was recorded. So that means the first station encountered the earthquake wave was 10 minutes apart, which is like roughly 100 to 150 kilometers away. Yeah. So the first wave recorded was P wave, and the amplitude of P wave, as you can see here, is very less, and these are the very easily it can be detected very easily, which we will see in the coming slides also. And then then after that, these are the these amplitudes which you can see here are the subphases of P wave. Okay, so what I mean to say is, now suppose whenever a wave encounters any kind of this unconformity or any kind of transition zone, like change in velocity, so at that particular point, the phases gets reflected and refracted, and a different phase of that particular wave is generated. So this is P, and this is some phase of some subphase of P. And again here also some sub phase of P, and then we have S wave. So S wave, what happens is S wave frequency is wavelength is high, and amplitude is also high, and it is also very easily detectable. But for earthquake waves, for seismological purpose, S wave is very easily detectable. But for active source, it's get very difficult to detect S wave because of the obvious reasons like noises, coherent noises, and noises due to a moving vehicle or any kind of wind or swaying of trees, you know. And again, and then these are the surface wave, and this is the end of the wave train. Okay, and this particular portion from here to here is called coda. That means that is the end of the wave train, and this is generally used for earthquake studies. So we'll not be discussing about coda or surface wave. We'll be focusing mainly on the P and S wave for coming classes. So we are clear up to here. Any doubts?
So I have a question, sir.
Yeah, please.
So which one is ground rule, sir?
What? Could you please, write it down? I'm not able, because my speaker or my speaker earphone speaker is not that it's not working properly. So if you could write,
Sir, I want to ask, which one is ground rule, sir?
Which form is ground rule? Okay, noise. It's a coherent noise. We'll be discussing in the coming sessions, and I'll also give you an example of ground rule noise in the coming slides. But we'll be discussing about noises during when I'll be discussing about the real case study, like processing of reflection data and modeling of the refraction data. Okay, so but in coming slides I'll show you the example of ground rules. Okay, here in earthquake wave, the noises are not that clear, because we'll be just focusing mainly on the amplitudes, and we don't bother about noises for earthquake waves. But for active seismic method, that is which we use in industry for imaging of the subsurface, for oil reservoirs, imaging of oil reservoirs and faults, will have to remove the noises. And we'll be discussing that in detail in the coming slide, in coming sessions. Okay. So, but for this is an earthquake wave. Okay. This is a single component earthquake wave. Okay. So here I will not be able to tell you which is the ground rule, but in the coming slide I have an example of real data set. There I can tell you the presence of ground rule, and I can show you also. Okay. Am I clear? Hello?
Yes, very clear.
Yeah. Okay. So based on now, I already told that there are two types of waves we have discussed, and so based on the based on the path followed by those waves, like we will be focusing mainly on the body waves. So the path followed by body waves decides the type of seismic method we will be dealing with. So seismic waves generally have reflection seismic method. There are two types of method in seismic, that is reflection method. So here also we will be focusing on the reflected phases and not the refracted phases. And then there is refraction seismic method. Here we'll be focusing on both reflection and refraction, correct? So for reflection seismic method, if I have a direct wave or a refracted wave, that will be taken as noises, because our main focus is only on reflections, reflected wave phases, correct? So for a reflected seismic survey, we'll be taking direct arrivals and the refractions, which you see here, as noise, and will remove those noises. Okay. Great. Let's keep it here. Okay. And for refraction seismic method, we consider everything, like from direct arrivals to reflected arrivals and the refracted arrivals. Okay. Now the next way. So before going into the types of before discussing the types of methods, seismic method, the basic fundamentals should be clear about on which principle the seismic waves which principle seismic waves follow. So as we have studied in during our schools and graduation, or like bachelor's degree in optics, or even in sound, for sound waves. So what happens is, whenever seismic wave also follows the same Snell's law. So what happens is, like, angle of incidence is always equal to angle of what do you call reflection. and angle of refraction depends. Here for seismic wave, what happens now? For seismic wave, what happens is whenever a seismic wave transmitted from denser to rarer medium, what happens is it moves away from the normal. Like now, suppose this is normal. So what will happen now? Suppose this is higher velocity and this is the lower velocity. That means that this is the denser medium, correct? Okay. So what will happen is the ray will be transmitted. Means after the incident ray strikes the interface, it will get reflected and refracted or transmitted. So what happens whenever there is a denser medium of a rarer medium? So what happens is that velocity will increase as the denser medium has higher velocity, and the refracted ray will move away from the normal, and again it will move and then get again it will go up and then get recorded by the geophone. And from Snell's law, we know that sine I, that is angle of incidence, and a sine of angle of incidence by velocity 1, that is that the V1, this is the velocity of that particular layer, is always equal to the sine R by V2, means the velocity of the reflected angle of incidence of the angle of refraction divided by the velocity of that particular layer, and which is equals to the refractive index. Here we call here we don't call refractive index, here we call ray parameter, that is R. Okay, clear? Okay. So I'm moving to the next. If you have any doubt in this, you can ask any question. If not, you can just type so that I can move to the next slide. Okay. So no questions. Move to the next slides. Now, there we saw only the simple case. Now, so in previous slide we saw a simple case. Okay. The ray parameter is not clear. Ray parameter is just like refractive index. Like now, suppose sine I by sine V1 is now suppose do you understand refractive index? Refractive index is tells you the refractivity of that particular layer, correct? So sine I by V1, that is of this particular layer, will always be equal to the sine refraction, sine R, that is angle of refraction by V2, that is velocity 2, and it is a constant. Like no matter for how many layers, like now suppose if you have multiple layers, so there will be multiple refractions, correct? So sine I by V1 is equal to this, then sine R1. Now suppose this is R1, so sine R1 by V2 is also equal to sine I by V1. Now suppose if I have one more layer, and that is that the refractive index of that is R2, so it will also become, now again it will be like sine, if I can write it, I could have shown by writing. So sine R 2 by V3 will also be equal to sine I by V1, sine R by V1 V2. So meaning to say that the refractive index of any layer will always be equal, like will always be constant. So for optics we go for refractive index, but here we call it as ray parameter, which remains constant for any media. I hope I made my point clear. No, have I made my point clear, or still there is a doubt? So if there is a doubt, then I can see if there is an option to write or something. Screen pointer. Understood. Okay, great. Then no. Now suppose this was the two-layer case. Like suppose only one interface is there. Now I'll be going to see seismic method follows all the rules of optics and sound waves, or okay. So we'll be discussing about those, so that when we talk of real data set, so it will not be a problem. Okay. Now here. Now here we see there is a source, correct? And there is a velocity of that particular layer, first layer, and then the velocity of second layer. And there, that means the V2 is greater than V1. That means that this layer is denser than this layer. Correct? Now, uh, this is the now suppose this is the ray diagram. Now when a wave propagates, it propagates as an envelope, like it propagates like packets. Okay, but for the sake of our understanding, we have used a ray diagram. So meaning to say that the rays will be ray will hit the interface with all the angles. Okay, now this is one angle, and this for that particular angle, this will be some refraction angle of incidence. This will be angle of. Can you again explain the relationship between incident ray density of a media ray passes through the angle of refraction? I mean, what situation which is the angle of refraction? Yeah, certainly. Now, if we talk of optics, okay. So what happens whenever a light hits coming from denser rarer media to denser media? What happens? The density, the velocity of the light ray decreases. Okay, and it bends towards obviously. Whenever, now suppose I'll give a very basic example and relating example. Now you are running on the beach. Now you went to a beach. You were running on the beach, and then you went into the water. What happens to your speed? It decreases, correct? So what happens? Decreases. That means the light will bend. Light. I'm talking about light now, not about the seismic wave. So what happens? Since the speed decreases, so obviously you'll the light bends towards the normal, means like see, angle of incidence will always be equal to angle of reflection. Okay, so as in Snell's law. Now angle of incidence will always be equal to angle of reflection because it's the same media. The density is and the velocity is not changing. So the angle of incidence will always be equal to the angle of reflection. And this is the normal. Now suppose an ray hit this particular point. So at this particular point, if we draw a perpendicular line, so that becomes our normal or point of reference. And from that, the rays get reflected back. Okay, so that particular so with the normal, the angle of incidence and the angle of reflection will always be equal because they are in the same media. Okay, but as the ray encounters as is transmitted to another media, what happens? Since the velocity changed, see now suppose if the density is high of that particular layer, so what will happen? Obviously, the velocity of the sound wave or the seismic wave will be high. And how can we know this? The sound wave or the seismic wave travel faster in the denser media. Now suppose you go to a railway station. Okay, so in railway station, what happens? You cannot, or you go to a railway track, so you cannot hear the train coming from. If the train is very far, you cannot hear. But the moment you put your ear on the railway track, you can feel the vibrations. That means what? The sound waves are traveling faster in the denser media, which we have already studied in our schools, correct? So that means the seismic waves or the sound waves which travel from rarer to denser media, since the velocity increases in the denser media, so in that case, what happens? The wave move away from the normal. Okay, but if it decreases, that means it will bend towards the normal, and if it decreases, that means it's a LVL, low velocity layer. Then suppose the velocity of this particular layer is 5 kilometers and the velocity of this layer is 2 kilometers. That means the upper layer is denser and compared to the lower layer. Okay, so the wave will move towards the normal and it will pass through this and it will not be generated in this particular layer. Now suppose here the velocity is high, it's a lot of to take. That's why I'll be discussing about LVL and the hidden layer case in the coming sessions. But just to clarify, so whenever a ray passes from rarer to denser media, seismic wave, it moves away from the normal. Okay, just because it has higher velocity. Okay, so understood. I hope I made my point clear. If I have answered your question, please type yes. Yeah, great. Now, as I was discussing, that the rays hit the ground or interface at different angles. So for every particular incidence angle, there will be a angle of refraction, correct? And likewise, and there will be n number of angle of incidence and angle of refraction. But for a particular angle of incidence, what happens? The angle of refraction becomes 90 degree. That means the ray grazes through the interface, along the interface, means angle of refraction becomes almost 90. That particular angle is called angle of incidence is called critical angle. Critical angle is nothing but the angle for which the ray starts grazing the interface. Grazing means moving along the interface. Okay, and that means the angle of refraction becomes 90 degree. Okay, and in any ray after critical angle will not be refracted. It will get reflected following the law of total internal reflection. So whenever angle of incidence is greater than critical angle, that particular ray will reflect back to the surface and it will not be transmitted. That means the total energy, whatever energy this particular ray had, which has a critical angle of incidence greater than critical angle, the same amount of energy will be reflected. Means there will be minimum loss of energy, means almost 90 degree or 90% of the energy will be reflected back to the surface, and which we it gives a clear amplitude on the data, which we will see in the coming slides. Okay, so far so clear. Understood? If yes, please type yes. Okay, so there is no question, so I'll be moving. I hope I'm not making the sessions boring, and you can ask me questions anytime. If you have any doubt, you can ask me anytime. Okay. Now, again, there is one more thing. We have studied the Snell's law. There is one more law that is called Fermat's principle. Okay, which you can take as an assignment. What are Fermat's principle and why it is important to study Fermat's principle? I'll type it here. Fermat's principle. Okay, so Fermat's principle indicates now. I'll show. So Fermat principle states that the rays take the shortest minimum path to reach the geophone. That means it negates paths taken by the rays through different layers and finally reach to geophone. Fermat's principle states that the lights or the not the light, means the seismic wave or sound waves take the shortest minimum possible path to reach the geophone or to the observer. Okay, so find about the Fermat's principle, and you can write a para about Fermat's principle and why it is important. Okay, so for that reason, so I wanted you guys to find out what is Fermat's principle. So for that reason, I did not put it here. Now, moving on to the again reflection and refraction method. I would like to talk about reflection and transmission. Also, I already discussed that the rays are reflected and transmitted to the different layers. Okay, how we comprehend where is the reflection and refraction, and what is the energy of reflected and refracted wave? Okay, and how we comprehend that there is a particular there is an interface at that particular layer. Okay, for that we need reflection, and we'll be talking about reflection coefficient and refraction coefficient or transmission coefficient. Now, the total energy transmitted or reflected. Suppose whenever I already talked about the energy of the ray in the previous slide for totally internal reflected waves. Now, all waves, the angle, now suppose the ray incidence like this. Okay, so it gets reflected and transmitted. That means energy carried incident ray is divided among reflected and refracted. Correct. And also, we see that there is a change in amplitude as whenever an incident ray hits the interface and then gets reflected and refracted. Since the energy gets distributed among these two, so obviously the amplitude will also be also change. Okay. Now suppose an incident ray has an amplitude of A1, A0, and the reflected ray has an amplitude of A1 and transmitted has A2. So how it can be used to compute the energy reflection coefficient or refraction coefficient. We'll be discussing in the coming slides. Now, of a particular ray is necessary to know. So that for the now suppose for industry or academia, what happens? We study the amplitude, how amplitude increasing as we move from short point to the further upset. So what happens? Then there is a decay of energy as we move down and horizontally and vertically. So whenever we move from short points, now in the I should 1 second. Yeah. So this is the source and this is the geophone. So whenever we move down or whenever ray is traveling, it is for obvious reasons. There is a decay of energy due to spherical divergence and attenuation or decay of amplitude. So these are parameters can be discussed with the help of acoustic impedance, that is Z, which is given by density of that particular layer and the velocity of that particular layer. Suppose this particular layer has a velocity v and density rho. This particular layer has velocity v2 and density rho 2. So the acoustic impedance will be rho into v, that is rho density into the velocity, and again for this density and velocity of this particular layer. Okay. So in contrast, if now suppose if this layer has impedance contrast of rho 1 v1 and this has rho 1 v2 rho 2 v2 and this has high density and this has less density, and so if this particular layer has lower density and this one has higher density, lower velocity, so what will happen? The acoustic impedance will be low for this particular layer, and if this is higher density and higher velocity, so acoustic impedance will be higher for this particular layer. So if you compute the acoustic impedance, so and for both these layers, so we will see a high drastic difference in the acoustic impedance. So wherever there is a change in acoustic impedance, that marks the boundary of our of the interface or interface dividing the two layers. So meaning to say that wherever there is a change in velocity and density, so we'll have to compute this acoustic impedance to know the presence of interface, any kind of interface dividing the two media. So higher the interface, that means the energy will be of reflected and refracted ray will be higher, and we can easily pick the phases or amplitude for that particular incident angle and refracted angle, which we will see in coming slides. Up to here, clear what is the acoustic impedance and why it is important? Hello?
Yeah, hello, which is
Yeah. Okay. So now we'll be seeing why how we can compute coefficient of reflection, means how much energy is carried for reflection and transmission. Yeah. So, excuse me. Excuse me. Now, as I already said, yeah. Sorry for inconvenience and excuse me. So what happens is the reflection coefficient gives the energy of reflected wave. Now in the previous slides, I already said the amplitude is A0 of incidence angle and A1 is for reflected. So if I want to compute the coefficient of reflection or the energy carried by the reflected wave, so what I have to do is we have to divide the amplitude of the reflected wave by the amplitude of refracted or of incident wave. But that is very difficult to compute, because amplitude versus offset is a very difficult domain of seismic data analysis. Okay, so for the sake of understanding, what we do is like the amplitude of the reflected wave is divided by the amplitude of the incident wave, but calculation of amplitude is very difficult from the seismic data, so we go for the acoustic impedance. So what happens is like the acoustic impedance of the lower layer, that is Z2, that is this layer Z2, and this one is the Z1. So Z2 minus Z1, like acoustic impedance of the lower layer subtracted by acoustic impedance of the top layer divided by the sum of both the acoustic impedance. So it will give us the reflection coefficient or reflectivity. Okay. So what happens is this is always higher or positive, always positive. Okay, most of the time, not always, but most of the time it is positive. Meaning to say that the we encounter denser medium as we go down. Means the top layer or the upper layer will always be rarer to the bottom layer or the okay. But in some cases this becomes negative, and why it happens and when it happens, I'll give an example. Now I talked about low velocity layer in the top in the second or third slide. Now suppose this layer has a velocity of 5 km per second. This layer has a velocity of 2 km per second. So what happens? This has lower velocity and this has higher velocity, correct? So obviously the density will be higher in this and density will be lower in this. So for this, what happens? Z2 becomes less when compared to Z1. So when we compute Z2 and Z1, and when we subtract, and then when we compute the reflectivity or reflection coefficient, obviously this will become negative. And for negative cases, what will happen is ray will not be generated through that particular layer. What will happen? There will be the ray will be refracted and transmitted. There will be no reflection in that particular layer, and there will be no generation of ray refracted ray also. The ray will simply pass. Like the ray will, now suppose this is generating through this particular layer, it will not be generated, it will simply pass, which I'll show you in the coming slides. Okay. And then and and also, so whenever there is a low velocity layer, that means the ray will not be generated, and the amplitude will see a phase reversal of 180 degree. Now suppose incident ray has an amplitude like this. So the ray which went into the refracted rarer medium, the amplitude will be just opposite of the incident ray. So there will be a phase shift of 180 degree, which we have already studied in our during our bachelor's degree. So I hope that's clear. So the transmission coefficient is given by amplitude of the transmitted wave divided by amplitude of the incident wave, and which can be given as like 2Z1, means double of the angle of impedance contrast of acoustic impedance of the first layer divided by the acoustic impedance of the summation of first and second layer. Okay. Now this is very interesting slide. Okay. As I already said, wherever wave is hits any kind of interface, there will be reflection and refraction, and there will be phase changes also. Remember that earthquake wave train I showed, like the data of an earthquake, and I told you that P wave, and there are sub packets of P wave and subphases of S wave and S wave and subphases of S wave. So whenever there is whenever P wave strikes interface for a particular incident angle or a particular dipping layer. Now suppose this is a horizontal layer, but there may be a dipping layer also. So that particular incident or dipping layer, there will be more mode shift. We say it mode shift in modeling. So the wave changes from P wave to SV, that is S vertical. Okay. Okay. Sorry. Now, so as we discussed in the previous slides, that whenever like whenever a wave is transmitted through different layers, what happens is like it gets like divided into sub phases. Like P wave will have different phases, S will have different phases. Okay, so here is an example of mode conversion. What is mode conversion? Mode conversion is a phenomena in which P wave gets converted into SV or SH. SV is like vertical, S wave propagating vertically down, that is SV, and SH is vertically, S wave propagating horizontally. Okay, clear? So we will have reflected and transmitted P wave for any P wave striking an interface, and we will also have reflected and transmitted S wave as well. And obviously, since S wave velocity is lower than P wave, so it will have a different angle of incidence and angle of refraction. Okay, so here the Snell's law doesn't work because we are talking about totally different phenomena of mode conversion. So Snell's law will only be applicable to same layer, same wave, that is P wave. Like here you can see phi1 and phi1. This is for P wave. Okay, but for since mode conversion is taking place, so the angle of incidence changes for S wave. Okay, hope I'm clear now. Okay, so these things are the basics of processing and modeling, which we will talk in the coming sessions. I hope this is clear. Yeah. Now moving on to the next slide. Now, yeah, I wanted to show you this. Now this is an example of a seismogram with a short point, and there is a basement or reflector, okay, and geophone, and it's connected to a terminal where the data is being recorded here, as you can see here, correct? So we have direct, now suppose there is a source, like it could be anything, dynamites, explosive, a thumper, vibrosis, sledgehammer. So what happens? So the once the dynamite is exploded or the short source is exploded, so the waves will be generated, all kinds of waves, P wave, S wave, and they will travel directly to the geophone. It will be directly to the geophone for all, like it will not move. Direct waves cannot move far offset, so we only see direct waves for a shortest distance. Okay, so we'll see direct arrivals, and then we'll see reflected waves. Now suppose this is coming and then getting reflected back to the geophones and recorded, and for each geophone we see direct. Now this is the direct arrival recorded by this particular geophone. So we see direct wave. This is the first arrival. Okay, and for these all geophones, these are direct arrivals. Okay, now again the waves are getting reflected and recorded by the geophones, so we see the reflected phases. And how we pick the phases, like we see there is a spike in the amplitude because there is a buildup of energy in that particular area. So that is why we pick the amplitudes, and we see the direct phases are always straight, and reflected phases are always hyperbola, no matter whether it is straight or flat horizontal layer or dipping. We always see that reflected phases are always recorded in form of hyperbola. Okay, because as we move from short point to the last geophone, and by the way, short point to the last geophone is called offset. Okay, offset means the distance of maximum recording. So as we move from away from short point to the maximum offset, the time of recording of reflected phases will be exponential. So that is why we see hyperbola kind of structure. and then there are refracted waves. So refracted wave will dive down, but it will not touch the reflector. It will go through different go through the depth or the thickness of the layer and get recorded, and it will again will be a straight line, but it cannot but sometimes it will be affected because of there are any kind of structure here, so it will not be straight line straight in that particular case. And we see now how we will differentiate between direct arrivals and refracted wave. Now, so you can see here the you can see some kind of a particular angle. There is a change in angle now, so it is making some kind of angle. Direct arrivals are making angle with the normal like this. Okay, now suppose this is 30 degree or 40 degree or 60 degree, whatever, but there is a change in angle here, correct? So that means I encountered a refracted wave. So there I'll stop with my picking of direct amplitudes, and I'll start picking the refracted waves or refracted amplitudes. Correct? Clear? Okay. So moving on to the next slide. If you don't have any questions, I'll move to next slide. So now all the fundamentals and basics of a seismic method I have covered. Mostly I have covered which are important for the for our understanding, and which will help us in processing and modeling of the data. Now moving on to the types of seismic methods. So I have already discussed that two types, refraction and refraction. In refraction method, what we do is we obtain the travel times of seismic waves. How we do that? In the previous slide, I showed this is the time, and this is the offset. So each amplitude has a particular time. Okay, so we pick the amplitudes, and for that particular amplitude, we have a travel 430. Sorry, what is 430? I don't understand. Okay, so
Oh, you can continue, sir. You can continue, sir. Sir, you can continue.
no. I said for refracted survey or method, we pick the refracted direct arrivals travel times or amplitude. We can say amplitude or travel time, because we are picking the amplitude, but actually we are picking the travel time. When the shot was fired and when it was recorded, so we have this particular offset or distance. We know the distance and we know the time of recording, so we pick that amplitude of that particular time. So we are picking the travel times of all the amplitudes for corresponding to all the phases and layers. Okay, and it helps in modeling the subsurface. We can model the layers, whether it is dipping layer, whether it has an anticline structure or syncline structure, which we will see in the coming sessions. And reflection method is generally used for delineation of oil reservoir or gas hydrates. Okay, here what we do is in reflection method we negate the direct arrivals and refractions. Okay, for reflected method, direct arrivals and the refractions become noises. We have to get rid of those things. We have only to focus on the reflections, and we pick the first arrivals only in that. So I'll tell you what are the first arrivals in the coming slides. Okay, so far so clear. And we have already discussed the reflectivity and how it will be helpful in delineating any kind of oil reservoir or gas hydrates present in subsurface of sea or land. Generally, land doesn't have gas hydrates. So again, here we have discussed the refracted method in what do you call it? In details. So I have already said that refraction method is generally used to image subsurface up to more like full crust. So depth of investigation is less, almost like 40-50 kilometers, and for that we have to have an offset of 200 to or more than 200 kilometers. So and in it cannot be recorded in one particular instance. So we'll have to be dependent on several short points with higher charge, means like we'll have to use a charge of 185, like 1000 to 2000 kilometers kgs of explosives. So it will go, since the charge size is huge, so it will go down and it will be recorded up to a far distance. Now suppose there is an earthquake, we now 200 kilometers, 300 kilometers away the earthquake occurs, so we feel that earthquake vibrations here also. So similar thing happens in refraction method. We plant dynamites, a few charges, and then we blast, and then we record the seismic wave generated with the help of several spreads. What is a spread? Now spread is a one bunch of geophones, like in one go, what is the distance of recording of the data can be done. So that is called spread. You can search about geophone spread in SCG wiki also. Okay. So surface waves, refraction method generally used to delineate any kind of faulted structure or shape of moho or dipping layers. Okay, meaning to say that for crustal studies and lithological studies, we do refraction method. Okay, and here also we use both P and S wave information, and we combine the P and S wave information to delineate any kind of lithological information, like what kind of rock is present. That can be done with the help of seismic data, P and S wave. We don't need well log data for crustal studies, because well logging is very costly and it cannot be done for a whole crust. Okay. We again, I talked here that the depth of investigation is always like up to moho, so we need a huge spread or offset to do that, to do the crustal studies. I'll be talking about this, and I'll show you the data of refraction service. So here what we do in refraction service or refraction service, what we do is we record direct arrivals, reflected and transmitted, and reflections also, and we have to pick all the phases from direct, refraction, reflection corresponding to all the layers. Mind you, the direct arrivals is only can be seen only in the top layer, not in the sub layers. Okay, so we'll have direct arrivals and then refractions and then the reflections, which we will see. This is a real-time data set. Okay, this is the jet component. This is a three component data set. I'm showing only the jet component, that is the vertical here. As I promised, that I'll show you PS and ground waves. So this is the P wave. You can see here it's not that clear. When I'll be talking about a case study, then I'll show you. This is the raw data, and the process data and the modeling data I'll show you. This is the P wave. Here we have direct arrivals and then refractions, then multiple reflections, and this is the S wave. Okay. Yeah, 1 second. Is there any chat? No. And these are the S waves. Okay. So for we need a special kind of geophones to record both P and S wave. Okay, so single component geophone with one spike can record only one component, that is P wave. It can be only P wave, it can be recorded. But for recording P and S wave and all the components, we require 3 component geophone, which we will discuss in the next session, because that is the what we call data acquisition session. And this is the S wave, and these are the ground rules, which you can see here and here. These are the ground rules dominating my data. These are ground rules. Okay. So I hope I'm able to answer the question of ground rules, and I should. Like the ground rules will always occur at the end, because they have very huge wavelength, and it will be. You can see it, you can identify it from the kind of wave train. Like now, suppose there is a P wave and S wave wavetrain is there. So it follows a P wave and S wave will follow a pattern, but the ground waves or the coherent noise or any kind of noise will not follow the wave pattern. That means those are noises, and we have to get rid of that for active seismic analysis, not for the earthquake or seismology. Again, I have discussed this. Can anyone tell me what is the time bound here? Type me because can you type, because I'm not able to hear what you guys are saying. Hello. Okay. So for refraction survey. So here again I'm showing you for refracted survey. We have direct traverse. It's not shown here. The reflection and the refraction are shown, and also I already showed this in the histogram above in the previous slide. Here I already showed like the direct rivals, refraction and reflection with the data, but here I'm just showing you the refracted wave and the plot of the refracted and direct arrivals. So now suppose why this is important, I will be seeing in the coming slides. Now this is the T1, this is the intercept time. The refracted wave mixed with the time slice, and this is the direct wave. And I already said that the direct arrivals will have a different angle, and whenever there is a change in angle, that means we have encountered a different interface, sorry, a different layer. So wherever there is a different layer, this pattern will change. Now suppose this is the direct arrivals, this is the refracted, and then again if suppose if there is one more third layer, so again there will be refracted wave. So the pattern will become this, means it will become slightly gentler. Okay, so for this we can compute the slope of this particular for this particular wave, and for this particular wave we can also compute a slope. Okay, we already know that is 1 by v1, that is the velocity inverse of velocity will give you the slope for this particular layer, or the top layer, and the second layer will give you the slope of this particular wave, refracted and direct levels. Okay, and wherever there is a crossover of the whenever there is a direct arrival and direct wave and refracted wave intersect, that is called critical distance. Yeah, critical or crossover distance. I'm confused. Okay. We'll see in the slides. Okay. And now we'll see an example and calculation of how we can calculate the depth of or thickness of that particular layer, which will be very useful when we talk about inversion and modeling. So we'll be seeing how we can compute the depth for a two-layer model. Now this is, now suppose this is a refracted wave. Okay, so consider this. Now suppose this is first interface and this is the second interface, and I have to compute the thickness of this particular layer. Okay, so what happens? Now suppose this is my source, or wave is generated, and then it goes here, and then again it gets received at this particular point. So it is forming a what? Trapezoid, correct? What is 420? I am not ignore that. 420 is nothing. I think there's a problem in my mic or something. My voice is not that clear. Yeah. You can ignore that. We get 420. Please ignore that. Now we have a case of geometry, correct? This is a trapezoid, okay, and we have angle of incidence and then angle of reflection, correct, and we have the velocity, correct. So if we extend this normal to this particular, and when we also have this x, okay. So using the formula of a trapezoid, can we compute this thickness of this particular layer? Yes, we'll be saying this. Now, time. Now, for that we have to compute. Now we have only two information, like x and the velocity. Okay, and we have time also. We have offset information. We have velocity information. We have time information. Now, so whenever a wave is recorded at the geophone, it is always a two-way travel time. Like it goes down and then goes up. So that means time taken by going down and then get again time taken by the to get received by the geophone. So it's a two-way travel time. So we know the time. So time taken by the geophone to record the what do you call signal. So what we have, like time taken by the wave to travel from S to A and then A to B and then B to G. Okay, so this becomes so from that we can compute the total time taken by the wave to travel from here to here. Okay, now again, so and what is time? Like how we can compute time? Time is equal to distance by velocity. Correct? Correct. So we have this SA. This is the distance, and we know the velocity v1. Again, there is a distance like AB. This is all based on the assumption, but it will help in computing our the thickness of that particular layer. But when we'll be talking about inversion and modeling, we'll be talking exactly how we can compute the thickness. Okay. So again, the second layer has a velocity VB, and we have the distance AB. So for TAB, time taken by the wave from to reach AB, we have distance by velocity, and again we have distance by velocity. So, and we have angle of incidence also. So can we can we compute, like now suppose this is the thickness Z1 we have assumed. So can we compute this like Z1 like we have the angle of incidence, and then for here also, and this is the 90 degrees. So can you compute all these things? Like ESD will become Z1 by V1 cos cos theta. Hello, understood?
Yes, sir.
Mathematics. So
Yes, sir. Yes, sir.
okay. So based on this, we are able to compute what ESD, time taken by the wave from traveling from here to here. Okay, so this equation will give me the time travel from time travel of the wave from S to G. Correct. Now from here we can compute what, and we know the offset also. We know X, we know V1, we know V2, we know this, we know X. Correct. We know TSD, time. See, time of we know the time also, because we blasted here and we recorded here. So we know the travel time taken. Correct. So we have TSG, we know X, we know our offset. Correct. And we know V1, we know V2. So can we compute Z1, Z, that is the thickness? Correct. Can we? Yeah.
Yeah, we can.
Yeah. So from this we can compute our the thickness. Okay. So this is what is done in the refraction seismic survey. We have to compute the thickness and the travel time and what do you call thickness of that particular layer. Okay. So again, this is clear because this is simple geometry and trigonometrical relationship. So I'm not going to discuss this. Understood? So moving on to the next slide. And again here also, now we know the time taken from here to here. Okay. But now suppose if I want to compute the time interval or time intercept time. So how would we do that? We have already computed the Z or thickness, correct? And we know the V2 and V1. So can we compute the interval velocity, or sorry, interval time, or time of taken by that particular now suppose if I have Z, V2, V1, so can you compute the T? Correct. We can compute because here we have already done it, right? So moving on to the next slide. So you can go through the slide and you will understand everything. So there is no need to discuss this in much detail, because These things are important for the coming sessions. So that's why I'm discussing all these things. Now, again, there is a concept of reciprocity in seismic method. Now, suppose for a seismic survey, if I have a huge offset, now suppose if I have an offset of 100 kilometers, so if I want to image a subsurface, how will we do that accurately? Now, there is a short point one here, the source is blasted and the data is recorded here. Okay, the data is recorded here by all the geophones, and these are the wave trains. Now, suppose see, you can see here, these are the direct arrivals picked, the first break. These are picked by the black dots demarcates that the data is the direct arrivals has been picked. And here also you can see there is a change in angle. So that means these are my refracted waves, which you can see here from like this. These are the refracted waves. So these have been marked or recorded. So I took the information from start point one and I modeled. Now suppose I made a model of subsurface from only short point one, but I don't know whether my this model is correct or not. So what I do is, now suppose again I had one more short point, and and it is recording the recording is in the reverse manner. Like now suppose this was the short point A for the short point one, and the offset up to here, and this is the short point to another source, and the recording is up to here. So what will happen? The traces or the pulses or seismic will be recorded up to this. So combining the information or the information on these two, we can utilize the method of reciprocity. Reciprocity to see to check whether my model is correct or not. So what will happen? So I have already modeled this and model the data from this. Again, I'll ignore short point one, short point A, and again I'll start modeling for short point B, and then I'll match whether my models for the two short points are correct or not. And if they are not, then again I'll combine the modeling of short point A and short point B to check if my where I can make the corrections. And so that my picking, these are the picking. See, these are the picking. The black dots shows the observed picking, and the lines show the computed picking, means done by the system or done by the following an algorithm. Okay, so if your observed and the synthetic or the computed response matches, that means your model is correct, and if they don't match, that means there is a discrepancy in the model. No. So I already said that wherever a direct wave or a refracted wave meets, that particular place is called crossover distance, and wherever reflection and that refracted wave extended meet, that becomes critical distance. Okay, these things are also important to compute the what do you call thickness or depth of particular layer. And this is the intercept time in the refracted wave makes with the time axis, that becomes the intercept time, which you can compute here. Okay, once you compute the jet, you can compute the intercept time. Now, we saw so many like we saw the this example of how to compute jet or thickness. Now, with the help of crossover distance and critical distance, we can easily compute thickness. Okay, this is with the help of intercept time, that is TI, and this is with the help of crossover distance. Okay, so you don't need to go in that much of complexity. You can simply, if you have intercept time and velocity information for both the layers, you can easily compute jet. And with the help of crossover distance also, you can compute jet. So far, so clear? Now, seismic, we are coming to an end, like 5 or 10 slides are left. So please bear with me. Okay, seismic reflection method. So why it is important? Seismic reflection method is generally used by the industry people, okay, to delineate any kind of salt dome, which are oil bearing zone, or any kind of faulted structure where there is a probability of finding oil and gas. Okay, and groundwater resources or any kind of stratigraphy with higher resolution, because depth of investigation is very less in seismic reflection method. So that means my resolution, we can use higher frequency waves, so that now suppose if the frequency is higher, it can resolve the subsurface for a shallow region. It can resolve the subsurface very clearly. So generally in reflection method we use high frequency waves, and high frequency wave cannot as they go deeper, like suppose if my depth of investigation is 5 kilometers of top surface, so we can use higher frequency reflected waves to image the subsurface up to 5 kilometers. But if my depth of investigation is up to more, like crustal studies, we have to take a lower frequency range of waves, because higher frequency wave will attenuate drastically or dissipate as it moves down. Okay, so reflection method is very useful for delineating stratigraphy, faults, folds, oil and gas reservoir, salt domes, groundwater resources, and as I told, it gives very high resolution image of subsurface. Okay, and it's cheaper than well log or drilling. Okay, drilling is a very expensive affair. Okay, so before approximation, how many minutes more? 10 to 20 minutes. I'll wrap up in 10 to 20 minutes. Okay. See, because I wanted to make this session very clear, so that we'll not be facing any problems. That is why I took more. See, and this is an example of reflected wave. I'll show about the processing steps and processing of this data and the stack section of this data in the coming year. So this is the data from KG basin, and see these are the direct arrivals and these are reflections, and this can be treated as noise. And you see this is the raw data and how noisy the data is, and we see how filtering and processing steps can make the remove the noises very and make the signals very prompt. Okay. Again, here is an example of a NMO, normal mover zero offset seismic data, and the stack section of that particular seismic data. This is called a stack section or seismic stack section, and this is called the zero offset seismic section. And this is not the zero offset seismic section. I'll show the zero offset seismic section for this also later. Now we have already seen in the previous slides, like for refraction, direct arrivals and the reflected arrivals. Okay, and refractions are always hyperbolic in nature. Okay, and it is given. These are generally the reflections. This is the zero. See, this is the zero offset reflections. Okay, in these are zero. See, whenever as we move away from the short point, the actual data is recorded like this. So as we move from zero offset, we see there is an hyperbolic structure. Okay, so in this they have what they have done is they have applied the NMO correction, normal move out correction, to bring the phases in zero offset fashion. So this is zero offset, and this is reflection, normal reflection, and this is again there is a reflection. So for zero offset we have this particular time interval, and as we move away from the start point, we have a hyperbolic structure. Okay. Again, here we can compute the travel time taken. So we already have the type. Again, so refraction, we had a trapezoidal structure, and we use the geometry of trapezoid to compute Z and everything. But here we have a triangle because reflection takes place at a particular point. So we have a triangular shape. And so, we already know that time taken is always two-way travel time. That is time going down and going up. So this is X, and if you want to compute time, so we can either take a half of the X total offset, or we can take 2D. Okay, X and 2D, or X by 2 and T. So it will give you the depth of that particular. See, we know the distance, we know the time, we can easily compute the depth. Correct? See, here is a depth interface. How we can compute. This is a simple geometry which you can apply, and you can get this formula, and we can compute the depth. I am not going to discuss this in detail because we have already discussed this for refraction survey. Okay, this is very simple. If you have any doubt, you can write it to me and I'll explain this. And okay. So as I already said that reflections are always in hyperbolic fraction, and T naught is the zero offset refraction. And as we move from zero offset, there is a increase in travel time, and it is denoted by del T. And we can see we can compute this del T as well, and this will help in doing NMO correction, that is normal move out correction, to bring out all the reflected phases in zero offset to get a stack section. Okay. See, this is how we can compute T like total time taken. So it is a amalgamation of zero offset travel time and del T, that is increase in the travel time as we move ahead. So it is very easily calculatable, which I have already shown in the previous slide. So you can easily calculate the time total two-way travel time for a receiver. Like suppose if the receiver is far, like for this particular, this is the short point, and if my receiver is here, so we can easily compute the time taken with the help of this formula. Okay. So again here, again this is the computation of two-way travel time. I'm not going to do the details of this. You can easily see, you can easily bring out see the maths. It will be understandable. If you have any doubt in this, I'll explain. If no, can I move to the next slides? If yes, then please type yes. And if you have any doubt, you can ask me. I can explain it now. Otherwise, it's very simple. So if there is no question, I'm moving to the next slide. Again here, how we can compute the del T. Yeah, how we can compute the del T, and why it is important. I have already said that del T will help in doing NMO corrections, that is normal move out correction. We'll have to remove the effect of del T to bring out this particular phase from here to here, that means in the zero offset fashion. So it helps in making a seismic stack section, so which we'll be seeing in the coming sessions. Okay. Now, types of multi reflection survey. There are many types of see, for refraction survey, refraction seismic survey, there is only one thing, like end on or what do you call it? A spread length, a split spread. But for reflection survey, we have many. There is split spread and single end to end. There is common depth point, common midpoint. We will see the example of all in the coming slides. This is the split spread. So short point will be in the middle, and this will be the detector. This is for the land survey, and for marine survey, we'll see in the coming for data, when we talk of data acquisition in the next year. So we'll be talking about land and marine data acquisition systems. This is end on survey. So there will be short point and there will be detectors. But there are many other surveys also that moving detectors and moving shots. So, and this is a short gather of reflected data looks like. Now, can anyone tell me where is the for a reflection survey, which one is the what do you call noises? So, as I discussed, now direct arrivals will be the noises, like these will be noises. So which data we have to concentrate? This one. These are the reflected data. So this will be my first break. We'll remove all these and we'll keep these while processing, and we'll pick the first break and we'll try to see. This is the zero offset, and as we are moving away from the short point, there is a increase in travel time and there is a hyperbola. So we have to bring all these reflections to zero offset in this particular layer. Okay. These are ground rules here. See, you can see here, these are the ground rules. So you can see here the amplitudes and the wavelengths are so high. Okay. So as I have already discussed, application of seismic survey is to delineate the subsurface lithology types of rocks, what kind of rocks are present, that can also be delineated. And civil engineers use seismic studies, or especially like surface wave studies to study the that particular regions to make huge structures, which are proofs. Okay. And seismic studies are also used in oil exploration, oil and gas exploration, and anticline syncline imaging, fault, and any kind of what do you call basement. Also, we can image basements, and presence of hidden layers and low velocity layers. So, seismic survey will give you the most accurate and most highly resolved image of the subsurface, but as compared to the gravity, magnetic, or any other geophysical method. Now, books to be followed are Fundamentals of Geophysics. Please note down, and you can get it from your library. And even if you have or online library of your universities, you can get these books, and this will be very helpful. Now, Fundamentals of Geophysics will teach you the basics of wave propagation, considering the seismology. Okay, so that is very important. So you must consult Fundamentals of Geophysics, and then this introduction to applied and environmental geophysics. This is also important. But for seismic, Philip Carey is the best book for simple understanding, because the language is very simple, and they have kept the calculation and numerical portion very simple, so that you can easily understand. And then there is Applied Geophysics by Telford, Gillard, and Sheriff. And the Bible of seismic, Bible, you can say Bible, Quran, Gita, whatever. But this seismic data analysis, Jose Ilmaz, is the best book for seismic. But this is for people who have better understanding of seismic method from earlier itself. Even I find very difficult to follow this book sometimes. So stick to these 4 books. And one more, stick to these 4 books. And once you master these books, then you can go for this Ilmaz. But for seismic processing, you can consult Ilmaz. Okay. So these are the assignments. I have shown you the calculation of Z for simple horizontal layer. So you have to compute for dipping layer ZB. Okay. And this is the reciprocity time. I have given you the hint also. And again, here Z1 and Z2 for we have seen for single layer. Here we have a 3-layer case. So you have to do that for single layer case using crossover distance and travel intercept time. Okay. So these are your what do you call assignments. So when we talk in the next class, I'll be discussing about this, and then we'll move on to the next slide. So thank you. If you have any problem or any questions, you can always write to me on this email ID, kumardeepak.at@gmail.com, and I'll be sending a copy of this talk to the convener, and you can collect it from her. And once again, a very well done to you guys for your effort, and for your effort to have these sessions for the betterment of for the students. I'm very happy to interact with you guys. Yeah, please, if you have any answer, please. Yeah.
Okay. Thank you very much, Deepak. Thank you very much, sir, for sharing these insights. Okay, Uzma, please, can you handle the question and answer session?
Near surface geophysics deals with only the surface waves. See, I'm not an expert in that particular domain, but near surface geophysics mainly deals with the surface waves, like Rayleigh and Love waves. And they try to image the kind of quality and the strength of that particular surface. And their near surface geophysics is mainly useful for civil engineering purpose, and for making for like any kind of huge structures which are which will be earthquake resistance to an extent. I hope I am able to answer your question, but I'm not an expert in that domain. So, and for near surface geophysics, we use a particular kind of software and hardware, like MASWA is a system which is used to acquire the data, and it is used for processing. MASW, MASWA, MASW. It's called MASW. We have expert in near surface geophysics also. A few days back, there was a talk by Dr. Nimisha Vedanti, right, Rodiak? No. We using geophysical instruments to get information of surface, basically not get it. No, we can. Now suppose, that's what I said. Now we have like based on our objective, depending on our objective, what is my objective, what I have to image, whether I am doing this for the purpose of making any kind of building or structure. So I'll go for GPR or near surface geophysics, where the depth of penetration is almost 50 to 100 or 100 to 100 meters. But now suppose if my intention is for all reservoir, like the depth of investigation will be 2 to 4 kilometers. So I'll go for a reflection or explosive data or air gun or water gun. Okay, and like vibrosis, thumper. And if my depth of penetration, like my investigation is, if my objective is to image only the subsurface up to Moho, then I'll go for a huge amount of explosives. See, I'm an expert in deep seismic and marine seismic. So we use explosive and air gun and water gun for data acquisition. But generally for deep seismic survey, like imaging up to Moho and below, we use dynamite and explosive of charge more than 1,000 or 2,000 kgs. Okay, and the waves are recorded up to a time for a time interval of 160 seconds, two-way travel time, 160 seconds. Like that is, if you take in one-way travel time, so that is 80 seconds. Okay, and with the help of that kind of data set, we can image subsurface up to 150 kilometers. But what happens is, the waves gets attenuated, the noises take over, so it becomes very difficult to identify the phases. Yeah. So based on our objective, we go for that kind of particular data acquisition, which will suit our objective. Okay. No. See, seismic wave, if we talk of seismic wave, earthquake waves are also seismic wave. If we see that with the help of seismic wave or earthquake waves, we are able to image the crust, mantle, inner core, outer core. So structure of how what is the depth of outer core, inner core, mantle, thickness of mantle, crust. Okay, so with the help of seismic wave only, we are able to image all those things. But yeah, in case for active seismic, okay, earthquake studies or seismology is called passive seismic. But what we do is, or what we are dealing now is called active seismic. So for active seismic, we do have the limit for penetration. As we said, see, for deep seismic, we have a penetration up to 60-70 kilometers, not more than that, because the waves can generate up to 100-150 kilometers, but it becomes very difficult for a geophysicist to pick the data corresponding to that particular depth. For that particular depth, like for 100 kilometer, it will become very difficult for me to identify between the noise and the phase. Okay, so we go up to the depth where we can find the phases with like with 100% certainty. Like suppose if I'm 100% sure that is okay, these are the phases and they are not noise, then I'll pick those phases. That means the picking of phases generally depend on from person to person or from geophysics, confidence on the geophysics. Yes, loss of energy due to the spreading attenuation and interaction of the. Yeah, exactly. The spherical divergence will be happening. Attenuation will happening. Everything, and even inelasticity of the material will cause attenuation of the data. Decay of amplitude will happen. There are many factors. Okay. Any more questions? We understand that it is refracted when it gets to the phase of media, different velocities. So, one second, one second. So, if the wave travels along the interface, what makes to be refracted to the surface? So, what you are saying is you are talking about head waves. So, and see, there is a difference between head wave and refracted wave. I'll show. See, here it's showing that the wave is refracted, but just for the sake of our understanding, I have drawn like this. But generally, this is the head waves. That means whenever there is a critical angle, I talked about critical angle, right? I talked about critical angle. So for critical angle, the wave grazes. So it will graze along the interface. So that becomes our head waves, and head waves are generated head waves will be recorded at the surface. So when a wave is like a head wave is grazing or traveling along the interface. So what happens whenever there is a dip? Now this is a flat layer, okay? But whenever there is a change in angle or orientation of the bed slightly, so at that the energy will or head wave will reflect back to or back to the surface. So, that is the concept of head waves, which I have not, because see, head waves are generally not important and we don't care about head waves. So that is why I didn't talk about head wave. Okay, and for a reflected wave, see, the question you asked that how reflected waves are refracted waves are recorded at the geophones. Geophone. Now, for a particular layer, now suppose this is my layer. So velocity is varying from here to here. It is not like that. Suppose this is V1 and this is V2. So the velocity will remain constant in this particular layer. Correct? So what happens is velocity is varying, like there is a gradient of the velocity, means velocity is changing at this particular layer, the velocity is changing drastically. Okay, means presence of another material. So what happens, the velocity is changing, and earth, see, earth is also not flat, earth is circular. So what happens, the wave whenever there is a change, see here also in this particular layer also there will be different types of rocks. So whenever a wave encounters a particular rock, so the behavior of that particular rock will change. And one more thing, this is just for the sake of our understanding, I am showing it for with the help of a ray diagram, but generally waves are generated in form of packets like this. I'll show you with the help of an video. I'll go out of this way. I'll show you. I'll show you. Now, yeah. Can you see this? Yeah. So we'll be seeing this. This is the example for earthquake. Now,
we can't see it, sir.
earthquake happened, and it is traveling in the form of packet or wavefront. Okay.
We can't see anything, sir.
What? You got it right?
We can't see the video. We can't see it. We are seeing seismic processing two methods, refraction and reflection. Your last screen.
Sorry, actually my mic is not working properly. So that is why I'm not able to hear. So please bear with me. If the information of the Earth's crust, mantle, and core was gotten through seismology, which source could generate such power for the equation? C. Uh, it's not visible. Okay, you can search on the YouTube how the waves are generated. So waves are generated in the form of wavefront or envelope, like a bubble. Okay, so this is just these are the ray diagrams. Just for the sake of understanding, I'm showing you these are the ray diagrams. Okay, but
concept of a seismic shadow zone as a global effect of an earthquake
yeah,
is
it's
an
a
oversimplification that ignores a broad array of refracted, reflected, and diffracted seismic waves that propagate through the earth.
One second, there is
For now, we'll just focus on direct.
no, not required. Okay. See, seismology, with the help of seismology only we can able to get the information of core, mantle, and core and mantle, outer core and inner core. But with the help of active seismic, we can not go more than 100 kilometers. So for with the help of active seismic, we can only image Moho and 30 to 40 kilometers below Moho. And for that, for imaging Moho and below Moho, like up to 100 kilometers, we use dynamites and explosive of huge charge. Like suppose dynamites of 100 kgs of dynamites are put together and then blasted in at once. So that will generate a mini earthquake, and it will the wave will travel through crust and below Moho, and then again gets recorded. Okay. Hope I made the. So please, can you might need to round up. So yeah, I'm done with my presentation. So if there are no any questions, I'll be able to answer your questions happily. With the you already have my email ID. So please follow that, and you can ask any questions based on that, and I'll be happy to answer all the questions. Thanks a lot. But please do the assignments which I have given. I'll forward it to Rodit, and she can forward it to all. Please do that assignment. Thank you. Thanks a lot. And it was great talking to you guys.
Thank you so much, sir.
Thanks a lot.
Brody, please over to you. So we sincerely appreciate Dr. Deepak. Thank you for sharing the insights with us. It was such an insightful section. It was very, very fundamental. We really appreciate that. So while I wait for Rodia to give the closing remarks, just want to say that as many of us that are here, SCG has a lot of benefits for us in case you are not yet a member of SCG or your chapter does not have an SCG chapter. We can actually help you set it up. You can just send us a mail at scgwestafricansection@gmail.com, and we'll be happy to assist you. And among the benefits of becoming SCG member, you have lots of opportunity. You get connected to the global world. You get knowledge just like the one that we had here. From the programs, you can be inspired to, make your career choices and you build your career in geoscience. And then SCG also encourages student leaderships, and volunteering as well. Then some of the benefits of SCG, you have scholarships, you have field camp grants for chapter, just like we are learning now. SCG can give your chapter a field camp grant to go and actually apply these things on the field. You also have technical program travel grants. If you have a paper to present, SCG can sponsor you to attend their annual meetings and present the paper. If you, SCG also have the Student Leadership Symposium where they invite 50 student leaders from all over the country to the SCG annual meeting. And we've had Nigerian leaders getting this travel grant. We also have the Student Chapter Excellence Program, the Most Improved, and the Best Student Chapter, So SCG has a lot in store for you. So if you are not yet a member of SCG, please, you just send us a mail at SCG West African section at gmail.com, and we will help you out. Or if you like to establish the chapter in your school, in your school, we can help you set it up. Yeah. So we'll share Rodiat is going to share the slides. I don't know if she's ready yet. She will. Rodiat, are you ready for the?
Excuse me. I have shared the PowerPoint presentation with Rodit. I have sent it to her mail. I'll be forwarding it to you guys, and please go through. And if you have any doubt, you can ask. Okay. Thank you.
Thank you, sir. So, Rodiat, you would like to say something else?
Yeah, I said, can you hear me?
Yes, we can hear you.
Are you done with the benefits?
Yes, yeah. You can add it. You can still add if you wish to.
All right. Hello everyone. My name is Rodia Kamuson from FUTA, and thank you very much for joining our training today. And I really want to thank Deepak Kumar also for taking time out of this Sunday to join us here. And I hope that everyone has learned one thing or another. And as you have started now, don't stop being motivated. I want to encourage you to, finish the training with us, join the Telegram, be active, look out for emails when we send updates or materials for you. And if you have any challenges, you can reach out to your chapter's president or to any of the presidents, or contact us on the email. We'll be dropping the email on the chat box. So maybe as already said, the benefits of SCG, you can join SCG even if you don't have a chapter yet at your university. You can still be a member of SCG. And apart from being those benefits that maybe has already said, you can also volunteer. SCG gives opportunity for students to volunteer through their SCG Wiki. It's like a page where you can publish your article, like some very simple topics that is not yet on the SCG Wiki before. You can publish it there. You can even volunteer for your chapter to help put their activities on the Wiki page. So and also SCG has this 360 mentoring 365. So you can sign up there and meet mentors. I didn't know Deepak from anyway. I met Deepak through Mohammed from Indonesia. He was the SCG president. It was through him I met Deepak, through SCG. And through Deepak, I've met a lot of people also that have been instrumental to my career journey now. So I just want to encourage you to not stop. And we will be posting other materials, the software that we'll be using in the next training. We'll be sending it to your emails. So look out for those emails. And as I've already said before, if you have any challenges, do not hesitate to contact us. So I don't know if there's any other president that wants to say something. Uzoma, Margaret, Tolu, do you want to say something or share anything to the participants?
Okay, good afternoon, everybody.
Good afternoon. You can hear.
Yeah. As the presidents have said, Mary and Rodiat have said, if we regard to the slide, my question is with you. Regards the slide, will it be shared to them on the Telegram group? Can you hear me?
Yes, we can hear you. We can hear you. Yeah, Deepak, please, are you going to give us the slide?
Hello? Can you guys are asking me?
Yes, I'm asking you.
Yeah, please tell me.
Can we get the slide from you?
Yeah, I have
do
already sent it to your email ID.
lecture.
I have already sent it to your email ID. Please check.
All right.
Okay. Sorry. Go.
All right. Okay, I'll share it with them. All right. So I want to thank everyone for joining us today. Thank you very much, and I hope that you've learned a lot. We hope to see you next week. We'll be starting on Saturday by 9 a.m. and on Sunday, as usual, by 3 p.m. But if you have, if you're going to have any constraint in joining, there is no problem. This meeting is recorded, and we're going to be sharing the recording with the participants. But if you still have any challenges, still email us. We'll get back to you. So, Uzoma, I'm handing over the mic to you. Thank you.
All right, thank you very much for that. And thank you very much, Deepak, also for this session. And also a very big thanks to every participant on the meeting. It was truly an enlightening period, also a fun period having you guys learn with us today. The comrades have said all, so our presidents from the different chapters have said all that can be said, especially from the vote of thanks and to the order of program. Well, I'd just like to chip in one or two things as regards learning. So this program is a series. So we've done the introductory part, which has to do with seismic, refraction, and reflection. And then upcoming will be the data processing and acquisition, and then a hands-on practical. So that being said, I would want
Uzoma, please unmute yourself.
So I said, I need us to have an open mind towards the learning process. You might not really grab all that you can, the concept and everything about it at once. So mind towards learning, and you get everything in. So a big one of us for joining in today. Big thanks to everyone, and we hope to see you in the next webinar. Thank you very much.
Thank you, everybody. See you next time. Bye. Have a great weekend and happy Eid al-Fitr to all Muslims. And happy holidays to the non-Muslims. Enjoy your weekend. Enjoy your holiday.
Thank you. Thank you very much.
Thank you.
Bye.
All right. Oh no.
No.